Good morning, students. Yesterday we discussed about the physical equilibrium, and now today we are going to discuss the chemical equilibrium. We have to discuss those chemical systems in which chemical equilibrium is established. Okay, so now let's have a reaction representing a chemical equilibrium. A plus B, I am taking a hypothetical reaction, is giving C plus D. A plus B, they are reacting. These are different reaction molecules and they are giving us the product. In case of reversible reaction, as I have already discussed this thing, that we have two processes taking place simultaneously. Okay, initially in the beginning of the reaction, A plus B, they are combining and they are forming the C and D. With the passage of time, what will happen? More and more AB will get consumed and C and D will get formed accordingly. So with the passage of time, what will happen? A plus B, it will get consumed, and C and D, it will get formed. If we plot a graph between the rate of the reaction and time, we will have it like this. This is the rate of the reaction, and this is time. So we have to see that what will happen to the rate of the reaction versus time. Okay, a rate of reaction. What is a rate of reaction? Rate of reaction means speed of the reaction. Okay, so what is the speed? At which speed the reactant molecules are reacting? They are combining to form the product. And in case of a reversible reaction, as you know, initially in the beginning of the reaction, A and B, we will have the maximum concentration of A and B. So at that time the rate of reaction will be maximum. So I should start from this point. This indicates that the rate of the reaction is maximum. But at that time, there is no C and D. In the beginning, A and B, we have maximum concentrations of A and B. So we will have the maximum rate of the reaction. But at the same time, in the beginning, there is no formation of C and D. So in the beginning, the rate of reaction for C and D will be 0. We can discuss this reaction in terms of two reactions. Like we have A plus B is reacting and it is forming C and D. This is one. Second, C and D is combining or reacting, I can say. It is going to form the A and B. So in the beginning, we have the maximum concentrations of A and B, so then the rate of reaction will be maximum. And at the same time, there will be no concentration of C and D. At the same time, there will be no, because at the start, in the beginning, A and B is reacting. Okay, so there is maximum concentration of A and B, so at that time rate of reaction will be maximum. But at the same time, there will be very less concentration of C and D, or I can say in the beginning there is no C and D, so the rate of reaction at that time will be 0. But with the passage of time, what will happen? More and more C and D will get formed. When more and more C and D will get formed, now they will combine and they will generate A and B back. So this will act as a forward reaction, this will act as a backward reaction. So initially the rate of reaction is maximum for the forward reaction, but this rate it will decrease. Why it will decrease? Because A and B is getting consumed. With the passage of time, the concentration of A and B, it will get decreased, hence the rate of reaction, it will decrease. But at the same time, C and D is formed more and more. So when C and D is getting formed more and more, they will react, and hence the rate of backward reaction, it will start increase. With the passage of time, the rate of forward reaction, it will go on decreasing, and the rate of backward reaction, it will go on increasing, and there will reach a stage at that point rate of forward reaction and rate of backward reaction will become equal. At that stage, we say that an equilibrium is established. So in the chemical processes, in the chemical reactions, an equilibrium is established when the rate of forward reaction becomes equal to the rate of backward reaction. Okay? So we can say this is the forward reaction, this is for the backward reaction, this is the rate of forward reaction is going on decreasing, this is the rate of backward reaction is going on increasing, and after some time we will have an equilibrium state. So an equilibrium state is established when the rate of forward reaction becomes equal to the rate of backward reaction. Now we will discuss the characteristics of equilibrium, chemical equilibrium. The various characteristics of chemical equilibrium are number one, at equilibrium the properties of system becomes constant. All the properties of the system at equilibrium, the properties of the system become constant. So at equilibrium, all the properties of the system become constant. Why so? Because you know, at equilibrium, if you take the reaction mixture at equilibrium, you will see that the composition of all the components, the concentration of all the components will be same. Okay? So that's why all the properties of the system will become constant at equilibrium. Number one. Number two, equilibrium is dynamic in nature. Equilibrium is dynamic in nature. It is dynamic in nature. What does it mean? It means that at equilibrium it seems to be that the reaction stops, but no. At equilibrium, as I mentioned earlier, that the rate of forward reaction becomes equal to the rate of backward reaction. Means the rate, the speed at which the reactants are reacting is equal to the rate at which the products are reacting. So at equilibrium, the reaction does not stop but takes place at the same rate. Number 3, reversible reactions, they do not proceed to completion. Reversible reactions do not proceed to completion. Reversible reactions do not proceed to completion. What does it mean? As we know that we were discussing this thing, that in the beginning the rate of forward reaction is very high because the concentration of the reactant is more. At the same time, the rate of backward reaction is 0. Why so? Because in the beginning there is no product formation. But with the passage of time, the rate of forward reaction, it decreases, and the rate of backward reaction, it increases, and there comes a stage at which both these rates become equal. So in these reversible reactions where the chemical equilibrium is established, they don't proceed to completion. Why they don't proceed to completion comes from the point that at equilibrium, the concentration of all the components which are there, they remain same, because the concentration, the rate at which the reactants are consuming in one direction is equal to the rate at which the other reactants are consuming, I mean to say product is consuming to generate the reactant back. I mean to say that at equilibrium, the concentrations of the reactants and products, they remain same. Why so? Because at equilibrium, the rate at which the rate of forward reaction becomes equal to the rate of backward reaction. So that's why these reversible reactions, they do not proceed to completion. Now we have the fourth. Equilibrium can be established. Equilibrium can be established in any direction. Equilibrium can be established in any direction. What does it mean? So we have the fourth point. Equilibrium can be, it's a basically characteristic of equilibrium. Equilibrium can be established in any direction. For example, let's take a reaction, N2O4 gas, it will give you twice NO2 gas. And if you take the NO2 as the reactant, it will give you N2O4 gas. So whether you start with the N2O4, it will lead you to give you the NO2, or you take the NO2, it will give you the N2O4. So whether you start with N2O4 or you start with NO2, in both the cases equilibrium will be established. So we can say that equilibrium, it can be established from any direction. So we have discussed some characteristics regarding the equilibrium. So now we will discuss, I will let you know the law of mass action, which we oftenly use in the chemical equilibria. Law of mass action. Law of mass action. Law of mass action. This law was given by two Norwegian scientists, namely Guldberg and Weg. In 1864. According to law of mass action, at constant temperature, the rate of reaction is directly proportional to the product of the molar concentrations of the reactants. For example, if we have a reaction A plus B giving you the product, then the rate of reaction is directly proportional to the molar concentrations of the reactants. And here we have reactants A and B, product of the molar concentrations of the reactants. So this was given by Guldberg and Weg. This is the law of mass action, which says that the rate of reaction is directly proportional to the product of the molar concentrations of the reactants A and B. So let us represent rate of reaction by R. In order to remove this proportionality constant, we will have a constant K, A, B. These square brackets represent molar concentration. Remember this thing. And what is this K? K is rate constant. K is rate constant. Now, if we have a more generalized reaction, like we have A plus BB is giving you let us represent only one first, gives you the product, then as I have shown you that the rate of reaction, it will be given by the rate constant, then molar concentration of A raised to power stoichiometric coefficient is called as stoichiometric. Small a and small b, they represent the stoichiometric coefficients, into capital B raised to power small b. To define more precisely the law of mass action, at constant temperature and at a given time, the rate of reaction is directly proportional to the product of the concentrations of the reactant species raised to power the number of molecules of the respective reactants in the particular reaction, in the given reaction. I will repeat. According to law of mass action, the rate of reaction is directly proportional to the product of the concentrations of the reactants raised to power number of molecules of the respective reactants, here A and here B, in the given reaction. And for the gaseous reactions, the law of mass action can be represented as AA is a gas plus BB gas is giving you the product. The rate of reaction is equal to K. Here we have to take the partial pressure into consideration, okay? Because we have taken the gas and we have different gases, so we have to take the partial pressure of the gas. So K, we will write partial pressure of gas A, okay, A times into partial pressure of gas B, P times. This is the law of mass action for the gaseous reactions. Now, let us apply law of mass action to the chemical systems involving equilibria. In case of chemical systems involving equilibrium, the law of mass action is used as, let's have a reaction AA plus BB is giving you, this is the sign of reversibility. Sign of reversibility is giving you CC plus DD. So here we have two reactions, the forward reaction and the backward reaction. For forward reaction, the rate of forward reaction, RF is the rate of forward reaction, okay, will be equal to the rate constant of the forward reaction, concentration of this reactant raised to power this, how many times it is present, into concentration of other reactant raised to power how many times it is present, or the stoichiometric coefficient. Call it as 1. Now the rate of the backward reaction means this and this is combining and it's getting you this reactant and this reactant back. For this we will write RB, rate of backward reaction, is equal to KB, this is the rate constant of the backward reaction. Here for the backward reaction, this and this will become as the reactant. So we will have C raised to power C into capital D raised to power small d. Call it a second. Okay, so this is for forward reaction and this is for backward reaction. This is for rate constant for backward reaction. Now, as we know, in a chemical, a reversible reaction, that with the passage of time, the rate of forward reaction goes on decreasing and the rate of backward reaction goes on increasing. And after some time, there reaches a state at which rate of forward reaction becomes equal to rate of backward reaction. And that state is called as the state of equilibrium. And at equilibrium, rate of forward reaction will be equal to the rate of backward reaction. So rate of at equilibrium, rate of forward reaction is equal to rate of backward reaction. So this will be equal to this, K forward into concentration of A, here is A, here is B, raised to power A into concentration of B raised to power B is equal to K backward, concentration of C raised to power C into concentration of D raised to power small d. Now K forward divided by K backward is equal to concentration of this C into concentration of D divided by concentration of A raised to power A into concentration of B raised to power B. This is at equilibrium stage, and this is equal to Q. This Q is called as reaction quotient. Okay. So this Q is equal to the ratio of the concentrations of concentration of C raised to power C, concentration of the D raised to power its stoichiometric coefficient divided by the concentration of A raised to power stoichiometric coefficient and the concentration of B raised to power its coefficient. So this Q, it can be evaluated, it can be calculated from the reaction mixture at any stage, but at equilibrium this Q becomes equal to K, and that K is called as equilibrium constant. So K, this at equilibrium we can write at equilibrium K is equal to Q, or Q is equal to K. So that at equilibrium Q is equal to K, so we can write K is equal to K forward divided by K backward, and is equal to, for the above reaction, C raised to power C, D raised to power D divided by A raised to power A into B raised to power P. So this is the result which we have for the chemical systems, for the reversible reactions involving the chemical equilibrium, which we have that equilibrium constant is given by the ratio of the molar concentrations of the products raised to power their stoichiometric coefficients divided by the molar concentrations or the concentrations of the reactants raised to power their stoichiometric coefficients. So this is how we apply the law of mass action to the chemical equilibrium, to the systems, to the chemical reactions involving the chemical equilibrium. Now let us see what is the effect of catalyst on the state of equilibrium. So now we have our topic, effect of catalyst on the state of chemical equilibrium. Effect of catalyst on the state of chemical equilibrium. So very important topic, very important topic. Now, as you see that we have a new term here, a catalyst. This is the topic, effect of catalyst on the state of chemical equilibrium. But we have a new term here, which is a catalyst. What is a catalyst? A catalyst, a chemical substance which influences the rate of reaction without getting consumed is called as a catalyst. A catalyst is a substance which influences the rate of reaction without getting consumed. That is called as a catalyst. We have various types of catalyst, like we have number one, we have positive catalyst, we have positive catalyst, we have negative catalyst, we have positive catalyst, we have negative catalyst, we have auto catalyst, and we have induced catalyst. So we have four types of catalyst here: positive catalyst, negative catalyst, auto catalyst, and induced catalyst. Okay. Now, what are positive catalysts? Positive catalysts are those catalysts which increase the rate of reaction. Negative catalysts are those catalysts which decrease the rate of reaction. I repeat, positive catalysts are those catalysts which increase the rate of reaction. Negative catalysts are those catalysts which decrease the rate of reaction. Auto catalysts are those catalysts in which product act as a catalyst. Auto catalysts are those catalysts in which product act as a catalyst. You are going for a reaction and you have some reactants and it is generating the product. If the product is acting as a catalyst, then that catalyst is called as the auto catalyst. And in case of induced catalyst, if one of the reactant in a reaction acts as a catalyst, then that catalyst is called as induced catalyst. Now, let us discuss some important points regarding the catalyst. Our topic is effect of catalyst on the state of chemical equilibrium, but we should know what catalyst is, what is the functions of it, what it performs. A catalyst, it does not change delta E of a reaction. Delta E is basically the difference in the energy of product and reactants. It does not change delta E of a reaction, number one. Second, a catalyst has nothing to do with the delta G of a reaction. And what is delta G? Change in the free energy. As you know that a reaction is spontaneous, means it will take place if it is delta G is negative, means there is decrease in the free energy. This catalyst has nothing to do with the delta G of a reaction. Number three, a catalyst will act on the spontaneous reaction, spontaneous processes. It has nothing to do with the non-spontaneous processes. And you know, spontaneous processes are those processes which takes place by itself or by initiation. This catalyst only affects the only the spontaneous processes, and it has nothing to do with the non-spontaneous processes. A catalyst, number four, it does not shift the equilibrium. It does not shift the equilibrium, but it will do one thing. It increases the rate of forward reaction and rate of backward reaction to the same extent. Number 5, a catalyst is specific in nature, means it will act on the particular reactions and it will yield to the product. It will not, a catalyst cannot act on all the reactions. No, it is specific in nature. Now, how a catalyst increases the rate of reaction? It's a question. It's a good question. The answer to this question is, it's believed that a catalyst takes the reaction in the alternate path in which the less activation energy is required. Let me explain this point with a graph. We have this is the potential energy. Here we have reaction coordinate. Reactants, products, this is the activation energy. This is a reaction in which catalyst is not used. We can say the uncatalyzed reaction. But when we add catalyst to this reaction mixture, then what will happen? It will decrease the activation energy. So initially the activation energy is more. Now the activation energy, now it will be less. Let's denote it by EA prime. Initially the activation energy is EA. It is larger in amount, but when we add catalyst, the activation energy gets decreased and we have EA prime, and EA prime is lesser than EA. This is the activation energy for the catalyzed reaction in which we use the catalyst. Catalyzed reaction. And this is the energy profile diagram for uncatalyzed reaction. So how a catalyst decreases the activation energy? It's believed that the catalyst takes the reaction along that path in which activation energy is less. And for that we have a theory called as activated complex theory. That theory says that when we have a reaction and that reaction without catalyst is taking place at a slower rate, but when we add catalyst into it, the rate of reaction increases. How so? We say that the catalyst, it interacts with the reactant molecules. When it interacts with the reactant molecules, they form some intermediates which are called as reaction intermediates. And those reaction intermediates have large amount of energy. They are highly unstable. Why they are unstable? Because they possess large amount of energy. And they have a transitory existence. Means their lifespan is very less. And whenever they are formed, they immediately get converted into the stable products and release the catalyst back. So, according to activated complex theory, how a catalyst increases the rate of reaction. It increases the rate of reaction by decreasing the activation energy. This decrease in activation energy which is taking place there is explained in terms of some theory called as activated complex theory, that says that reactant molecules interact with the catalyst and they are going to form some intermediates, and those intermediates, they are also called as reaction intermediates or intermediate complexes. They are very much unstable because of high energy. They immediately get converted into the product and leaves the catalyst back in the original state. So now we have the information regarding a catalyst, that what is its role and how it performs its action. Now we can discuss the effect of catalyst on the state of chemical equilibrium. Suppose we have a reaction A plus B is giving you C and D. A plus B is giving you C and D. A and B is getting consumed and it is forming C and D. And when this small amount of C and D is formed, that C and D will react, some of the molecules of C and D will react, and they are going to form the A and B. But what catalyst perform? When we add catalyst, so without catalyst, this will have some speed, this reaction will proceed at some speed, okay? But when we add catalyst, that catalyst, it will increase the rate of forward reaction and also the rate of backward reaction to the same extent. So the state of equilibrium, it will be achieved faster, okay? So without catalyst, equilibrium will be established. It will take some time, but when we add catalyst, the state of equilibrium, the stage of equilibrium, it will be attained very fast. So the take home message is, or the crux of this topic is that the catalyst, it has effect on the chemical equilibrium. How? It increases the rate of forward reaction and the rate of backward reaction to the same extent. Then what will happen? The equilibrium state or the equilibrium stage, that will be attained at a faster rate.